Welcome back to Integral Calculus. In this video, I want to talk about the area between two curves. Let me get my head out of the way. I'll dive right in. You should remember from your previous study of calculus that if you are looking at the graph of a function, and you pick a couple of points on the graph, say x equals a and x equals b, then the integral from a to b of that function is the area trapped between that function and the x-axis. So you can calculate that area by setting up an integral, which is great if you have one interestingly curved side and three perfectly straight sides in the figure that you are trying to study. But it doesn't have to be that way. Let's jump over here. This is a graph that I have on the website Desmos, desmos.com. I've just given us a couple of functions. In blue, we have this parabola. F of x is x squared plus 2x plus 1. In orange, we have the line, g of x is 2x plus 5. These two intersect each other at this point here and at that point there, giving us this very interesting region in the middle whose area we might want to calculate. Let's jump back over to my notebook and let's start digging into what we can do with those. So just writing them down again. F of x is x squared plus 2x plus 1. G of x is 2x plus 5. And I guess the first thing we want to do is figure out where the intersections are. And sure, we could do this in Desmos. If I jump back over to Desmos, one of the things I want to remind you is that if you just click on the graph, it allows you to come up with the points of intersection. In this particular case, those are fairly straightforward integers, but if they weren't, you would have to do this by hand. And so, just a quick reminder that the intersection points are the points where the y values are equal. So if we just take one function and set it equal to the other function, I can, well, let's subtract 2x and subtract 1 from both sides of this equation, and then use the square root of property to say that x has to be positive or negative 2. It's not that difficult to go through for relatively simple curves, which is all we're going to be looking at in this course, and we can get exact values that way. If the curves were more complicated, instead of trying to get exact values, I'd probably just go ahead and use the numerical approximation. I would probably also at that point be using numerical tools to do the integral as well. But I want right now to focus on doing this by hand because understanding the how and why I think is kind of interesting. All right, so the curve that was on top was g of x. If I calculate the integral from -2 to +2 of g of x dx, that will give me, everything below that line, which includes all of the area that we care about, but also includes a bunch of other stuff. That's why we also look at the parabola. If I calculate the area under the parabola in the same region, I will get all of the stuff that I overcounted before. So if I just subtract those two integrals, it will give me just the area of the stuff in between. This is exactly the same thing that you've done in a high school geometry course or something like that, where you had, say, a rectangle that had a circle cut out in it. You calculated the area of the rectangle, you calculated the area of the circle, you then subtracted them to get the area of what was left behind. In this particular case, we could just go ahead and do these integrals, but it is interesting to point out that because they are the same limits of integration and they are the same differentials here, we can actually combine these. In your previous study of integration, you probably more often went the other direction. You started with the integral from -2 to 2 of g of x minus f of x, and you split it up. But split it up, put it back together, it's all good, it all works. I don't want to scroll down yet because I need to know what my functions are so I can plug those in. So we've got the integral from -2 to 2 of 2x plus 5 minus x squared plus 2x plus 1 dx. And going through simplifying that algebra a little bit, this is going to turn into the integral from -2 to 2 of 4 minus x squared. That's a fairly straightforward integral to take care of. You're going to have 4x, you're going to have 1/3 x cubed. You're going to evaluate at the limits of integration, -2 and +2. All right, plugging in the upper limit of integration, 4 times 2 is 8. 2 cubed is also 8. So we've got 8 minus 8/3. And then we've got -8 plus 8/3 when we substitute in the other limit of integration. So I guess this is going to be 16 minus 16/3. All right, well, 16 is the same thing as 48 divided by 3, and 48 minus 16 is 32. So the area between these two particular curves is 32 over 3. Let's go ahead and look at another example. Here this time, I have the functions f of x is x minus 1 cubed, and g of x is x minus 1. And the thing I want you to notice about these functions is they kind of swap places. There we go. So if you look here, down here, between between 0 and 1, the blue curve f of x is on top, the orange curve g of x is on the bottom. And if you come over here, the blue curve f of x is on the bottom, and the orange curve is on top. And so you have to stop and think a little bit about how to set this up. Well, the way I'm going to approach it is, let's just look at this part. We'll just look at the area between the two curves here. And then let's just look at this part. We'll look at the area between the two curves here. And then we can add the total areas together. So let me get my head out of the way and let's look at just that. We want between x is 0 and x is 1, f of x was on top and g of x was on the bottom. Yeah, I could have written this out as two separate integrals and subtracted them and brought everything together, but you saw that happen in the last example and I'm too lazy to write it out again. But then, between x is 1 and x is 2, the two curves go in the other order. G of x is on top, f of x is on the bottom, and so we get that. I'm also going to take the time before I plug things in to come back up here. X minus 1, the whole thing cubed, is x cubed minus 3x squared plus 3x minus 1, making sure I got the signs right there. All right, so when we take f of x minus g of x, it'll be x cubed minus 3x squared. Nothing will happen there. Then we have 3x minus x, which is plus 2x, and then we have minus 1 minus minus 1, which is 0. So there's that. And then when we subtract in the other order, we'll get the same terms. They'll just all have their signs flipped, from positive to negative, from negative to positive. So it'll be minus x cubed plus 3x squared minus 2x dx. Right. You may have noticed geometrically that these two shapes look identical. There should be some symmetry in these graphs, and so these integrals will probably come out to the same numerical value. But just for this example, I'm going to go through and do those steps carefully so that I can prove to myself that that's the case. All right, so integral of x cubed is 1/4 x to the 4th. Integral of 3x squared is x cubed. Integral of 2x is x squared. The second term, we have the same things, they're just in different orders. Changing positive to negative, negative to positive, and of course we have different limits of integration. All right, so evaluate when x is 1, we'll have 1/4 minus 1 plus 1. Evaluate when x is 0, we will have 0. Evaluate when x is 2. Well, 2 to the 4th is 16. 16 divided by 4 is 4, and that was negative. So we have negative 4 plus 8 minus 4. And then when x is 1, we have negative 1/4 plus 1 minus 1. So 1/4 minus 1 plus 1 is just 1/4. I'm going to go ahead and keep that minus 0 in just for a moment so that I can remember that all of this was the area of the first kind of loop of the figure. And then over here, we have, well, minus 4 plus 8 minus 4, all told that's 0, minus negative 1/4 plus 1 minus 1 is negative 1/4. And again, all of this is kind of the second loop. And as I said when we started off here, the area there, 1/4, and the area here, 1/4, are the same numerical value. And of course, 1/4 plus 1/4 is 1/2. All right, one more example here today. If I jump back over to my graphs in Desmos, you can see I have the functions f of x is 4 minus x squared, g of x is x minus 2, and h of x is negative x minus 2. I have three curves here. And what I want you to notice is that if I had just considered f of x and g of x, I've got this parabola, I've got this line, and there is a space between. It looks kind of similar to the space we looked at in the first example. If I had just looked at the parabola and this line, well, there's another. Here's a space between. It looks kind of like we did in the first example. But because I am bounding my region by all three of these, well, there's a couple of places I might be looking. I might be looking here, I might be looking here, or I might be looking here. And so the instructions are going to have a little bit more information. In this problem, I'd probably say, calculate the area of the region containing the origin. Well, here's the origin. It's contained above by the parabola and below by each of the two lines in different parts. Just like in our previous example, we can figure this out by splitting the area in half. In this case, I'm going to split in half along the y-axis, if I can get my hand mostly out of the way, but still there. All right, so when x is negative, in this part of the region, I'm bounded above by the parabola f of x, I'm bounded below by the line h of x. Over here, where x is positive, I'm bounded above by the parabola, I'm bounded below by the line g of x. And so that's the information that I need. I suppose I also need that the intersection points are at -2, 0, +2, 0, and the origin. You can go through and figure those out, do the algebra on your own if you so desire, but these are some nice whole numbers, so that makes life easy. All right, so I've got f of x is 4 minus x squared. I've got g of x is x minus 2. I've got h of x is negative x minus 2. And I know that the area here, well, the part in the negative x-axis went from -2 to 0. Remember, it had f of x on top, it had h of x on the bottom. And then the other part from 0 to 2 had f of x on the top and g of x on the bottom. And so I just have to fill these things out, clean them up a little bit. So we have 4 minus x squared minus x minus a minus would be plus 2. So I guess that's 6 minus x squared. For this first integral, we have f of x minus h of x. F of x is 4 minus x squared, h of x is minus x minus 2. We are subtracting, so positives and negatives are going to get really messy. But we have 4 minus -2, that's 6. We have minus negative x, that's plus x, and we have minus x squared. For the second integral, we have f of x minus g of x. So 4 minus -2 is still 6. We now have minus x, and we have minus x squared. All right. Once again, there is a symmetry argument you could make here. The figure that we are studying is symmetrical about the y-axis. So if we just did one of these integrals and then doubled it, we would get the area that we need. But I'll take the time to work out both because it doesn't take that much effort. All right, so we're going to end up with 6x plus 1/2 x squared minus 1/3 x cubed, endpoints -2 and 0. We're going to end up with 6x minus 1/2 x squared minus 1/3 x cubed, endpoints 0 and 2. All right, plug in x equals 0, you get 0. Plug in x equals -2, you get -12 plus 2 and then plus 8/3. Then let's look at the second integral. Plug in x equals 2, you get 12 minus 1/2 times 2 squared is 2, and then minus 8/3. Plug in 0, you get 0. All right, so numerically they are the same values. They have swapped positive and negative between those two, but of course there's the negative out here, which is giving us exactly what I thought we were going to get. So we've got, all told, in that first grouping, 10 minus 8/3. We've got all told in that second grouping, 10 minus 8/3, which is the exact same value. I guess we have to figure out what that is now. Common denominator of 3, so we'll have 30 minus 8, which is 22. And we've got 2 of them, which all told will be 44/3. All right. So here's some functions that I'd like you to think about. I have here f of x is equal to 0, g of x is equal to x, and h of x is equal to 4 minus x. These are all straight lines. Because they're all straight lines, you could probably do this without using any calculus whatsoever, but I want you to use this as an opportunity to practice calculus. So, first of all, use Desmos to graph all 3 of these functions. You should see that there's only one region bounded by all 3 of the functions. And then set up the integral and evaluate the integral to calculate the area. Take a couple minutes, see what you can do with that, and I'll see you in the next video.